Okay. Hey, how y'all doing?
Good,
I
good. How
can't.
are you?
Doing well, especially because I can hear, which is better than not hearing. So there's one thing, and I want to make sure that I've got chat open in case someone needs to chat. Okay, unless any of you have a reason that I shouldn't, I'm going to start by just sharing a screen and doing the things that, like the last couple days, we do. Okay, there we go. And just maybe a couple administrative things. One of them is, gosh, I hope that you saw this and paid attention to it and don't need to see me right after class. But if you do, just flag me right after class ends and say, wait, 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 don't shut it down yet. So that's a good thing. One of Also Monday of next week. Again, office hours normally on Monday are like between the two classes, but there's one like at 1, and then there's another one that's at 3:25 to 3:50. But no, it'll be 3 to 3:50 on Monday of next week. Also want to sort of draw your attention towards there's this exam thing at some point in time coming up. I guess I should find out when that is because, I should write a test. It's not clearly yet, but if I'm looking at the calendar, I'm thinking, oh my gosh, that's pretty darn soon. And so, yeah, material in chapter two, the first couple bits today. Next couple bits is on Monday. And then the exam does not cover material in chapter three, sections one and two. It's material that matches our chapter one and two. The exam will be made live, probably right following class on Tuesday of next week, and it'll be due 2 days later, Thursday at 11:59 p.m. So if you're feeling solid on chapters one and two, you should be in good shape. Another thing is I talked to the grader today, and you got homework due today by midnight. And then I'm going to have the answers online or posted online for y'all as of tomorrow morning at some point in time, early-ish. And the grader might start grading the homework as soon as tomorrow, but we'll find out. Okay, so that's where I think things stand. You, however, may have some administrative questions, which I'm happy to answer.
Is the exam like multiple choice and we submit our like written work, pictures of our written work?
Hmm. Yeah, great question. I think with this class, what I like to do is to have it such that the bulk of the exam can be Canvas, right? But in some cases, you might want to submit, like you suggested, written work. And usually, the way I've liked to do this in the past is a student will often write out their stuff by hand on a piece of paper and then just take a picture of that. Then you could sort of like put that into a PDF and upload the PDF. Or you could also incorporate, screenshots from JMP if you wanted to into a PDF to sort of justify part of your answers. So yeah, it's my attempt to do something close to, if not the equivalent of, an on paper exam. So yeah, because of the nature of it, some of the questions will be looking for a number, some will be multiple choice. But in any place where you think I would like to explain my reasoning because I would like partial credit, you should always feel free to upload something, and there will be a place to upload a PDF as part of the exam. And so, yeah, I think the exam will be like nominally a 50-minute to or an hour long exam, but I'll give you an extra 5 minutes for the uploading of the file. Does that answer your question, Magna?
Yeah, it does. Thank you.
Cool. Anyone else?
Will there be any practice for the exam, like recommended questions from the book and
Yeah,
etc.?
yeah, great question. Let's look here under exams, clicking my way into that. I don't know if there's anything for exam two. Oh yeah, it looks like there's something there. Let's see if it's live. The so from the sample exam from 4 years ago that I think was good for them, and this is a sample exam where I literally gave, the same sample exam 2 years ago when I did the class online. So I've got answers written to this is if it were an in-class in-person test, you do it on paper. It's not. And so I've got some brief answers. I didn't apparently upload the brief answers, and the full answers are here, but I don't want to show them to you because that would be bad. I will upload the brief answers later. So that way you can sort of see a quick numeric thing. Because some students a couple terms ago said, you know what? Don't show me the whole worked out thing. Just tell me numerically whether I'm right or not. So the brief answers will be there for that. So that gives you a sense for the style of the exam that I would typically have, and you could prep from those. And any questions from those sample exams, okay, or from homeworks or labs are really good for the sake of learning the material, and they're great for office hours. So, any other questions? Oops, sorry. That was my notes for the day, what I want to speak to. Okay, so if there aren't any other questions, I think we're moving forward in chapter two, section one, and we should finish up 2.1 and 2.2 today. And then the lab is covering chapter two, section two. And so many of you have been in a stat class in the past, and you sort of saw perhaps an equation for the standard deviation. You might have wondered, why is there an n minus 1 instead of an n in the denominator? The lab today is an attempt to sort of get you to confront that issue, understand the standard deviation a little bit better, but also maybe learn something about why the standard deviation has that n minus one. It's an attempt to do a better job estimating an unknown true population standard deviation. So, sort of getting into newish content here, I want to sort of go back and say our textbook is unusual in that most books will start with not the pictures like a histogram and then distributions, but they'll define like probability and then somehow we'll go into measures that describe data. Our book that puts these things in a slightly different order, and there are some real benefits to that, along with some challenges. But I'm going to be positive today and say I like the book, and even if it's not the standard order that everyone goes with, I think it still makes a lot of sense, especially because you already know what an average is. We should still probably define the terms that we use. So let's go ahead and do that. So, location. If I'm trying to describe where the data are, I'm describing a measure of the location. And those things are like a mean, and we will term the mean X bar if it's data, or maybe the median. And I'm not going to sort of tell you a symbol for the median. I'm going to say the symbol for median sort of differs by book. Usually we just write median. But if I have the question, where are the data? Like if I have a list of heights of people, maybe let's even just start. And let's open a data set that may be something not there, but a recent data set. Okay, yeah, you dealt with the firefighters in the lab. Let's go back to them. And let's look at the distribution of the ages of the individuals in the data set. And I'm going to ignore the fact for now that one firefighter occurs several times. If I just have a list of ages and I want to know the average age, right? I would use analyze distribution. Tell me about then the ages. Drag that over here. Click OK. And you're going to have shown to you both the histogram like we did last time, but you might have spotted things like, oh, you're also told the mean age of the numbers in our list of numbers. It's 39.79. And that's not even an age that if you ask a person, how old are you? They're never going to say 39.79. They'll say, well, 39. They're going to round down. So if we take our ages and calculate an average of the ages that had already been rounded down, we don't need to round down again. We're just going to say, here's the average of these ages, right? So average, it's the mean. Let's go ahead and talk about, maybe I'll do it this way. Let's go ahead and define the terms that we have. If you've got data values, X1, that's the first one. X2 is the second one. X3 is the third one, all the way up to Xn. That is the nth data point. In general, we say we have n data points in a data set. And looking at the data here, here's X1, the first age, X2, X3, X4, all the way through the end of my list of numbers. Oh my gosh. Oh, wow, a lot. X 474, if you will, X 474 is that 25, and X1 is that 29. 29 right there is this guy. Okay. So we're just defining these values so that way I can then say my definition of the average, the mean X bar is X bar 1 over n times the sum of those x values. I goes 1 up to n, xi. Let's rephrase that. You're going to want to add them all up. Just add up all of the data values. Add them all up and then divide through by the number of terms you added together. Now you're comfortable with that. You've all done this before. You've all seen the definition before, most likely. What about the median? Median is also something that most of you have seen, but let's give you sort of an approximate way of defining it. Our book has a slightly different approach, which is right, but I think here's the way I prefer to find the median. We're gonna, for the median, we're gonna first off sort the data. And I go low to high. If you went high to low, that would make sense too. But I prefer low to high because that's sort of what we typically do when we sort things low to high. And if I have n data points in total, so after sorting the data, second part of this is find n plus 1 over 2. And the n plus 1 over 2th data point is the median. If I put them in order, lowest to highest, n plus 1 over 2 is then that median data point. So let's look back at our firefighters again. I've got them right here. Maybe I'll make this smaller so we can see it right here. And analyze the distribution. Clearly, sorting them lowest to highest is not sort of the easiest thing to do, but if I take the ages and I want to know about the ages, click OK. I sort of don't have them here, but one of the things we have in our stem and leaf diagram is the ability to sort of get the data in order. So I'm going to stack that up so I can stretch it out. And then I'm going to turn on the stem and leaf diagram. This is not because you have to do it this way, but if you have you've got 400 some values, oh my gosh, 474 values, the stem and leaf diagram might be a quick way to find that median. So 474, our equation says 474 plus 1, divide through then by 2, 474 plus 1, 475, 475 over 2. What is that? 475 over 2, I'm in my head, it's 240, 239, 238, 237.5. I'm going to find the data point 237.5 in my data set. And if I'm going lowest to highest, maybe I'm going to move this up just a little bit so I can write more easily. I've got 2 here. I'm at a total of 6. I'm at a total of 19. Plus another 17 is 36, 56. Uh, A is 83. Plus another 29 is 1, oh, whatever. Could I go up, cumulative adding up the number of until I get right at then the median value? Yes, you can. On the other hand, some of you are thinking, idiot, why didn't you just look at the output where it says the median is right here at 40? Yeah, literally, if we had the data values in a software package, the median is going to be easy to get for free. The
Um,
median value. Yeah.
can you go over what the exponent is for the n plus 1 divided by 2? Is
Oh,
that
yeah.
positive n?
No, it is not an exponent. It is just the location n plus 1 over 2 th. Or if you don't like th, let's go with d, the 52nd data point. It's just telling me the location, the data point at location n plus 1 over 2. The data point, if I had the list sorted from lowest to highest, if I go up to 275, no, 237.5, I'm going to have somewhere between the 237th and 238th. I will be where I'm going to find the median.
Oh, okay. Thank you.
Yeah, and it's going to be one of these guys because we saw that it is indeed a 40. So if median, basically think if you lined up the players on a basketball court who are playing for one team, there's usually the point guard is usually the shortest, not always, and then you're going to go with the shooting guard, then the small forward, large forward, and then the other large forward because we usually don't have centers. But if you line up the players in order, it's the person in that 3 spot who's going to be the median height player. Okay, any questions about the median?
Sorry, out of curiosity, can you pull up the 237th point five point again on the chart just so I could see it? I just didn't see it.
Yeah, it's not really easy to find, but I'm going to say if you do a cumulative sum as you go up, yes, you're going to
Oh, I was
have
wondering
like
about
2.
the column, just the
Oh, okay, yes. This is a column that has not been sorted.
oh, okay.
So if I find the 237 237 and 238, you'd think somewhere between 27 and 27, but the problem is we hadn't sorted them first. Now there is a way to get JMP to do the sorting, but if you got the software already here in front of you and you say summarize the distribution, you get the median for free. It's 40. I'm good. Don't have to do it by hand.
Okay, thank you.
Yeah, good question. I'm glad you asked. Um, Anyone else? Okay, so what I'd like to do is to say, what if we are now wanting to relate what we know from last time, the distributions, to right now, and maybe 2 times ago. How would I look for that connection? And I'm going to say, well, what if we have a symmetrical distribution? So I'm going to try and draw, this is like a bell curve, but I could draw other symmetrical distributions, like maybe a pair of bell curves. The mean is literally the point of balance. X bar is the fulcrum. And so, we're going to balance right there as well. I tried to draw this symmetrical. I apologize. It wasn't perfect. There we go. Closer to symmetrical. So the point of balance is where the mean is going to be found. The median, and I'm going to go with orange for the median. The median is where you have half of the data values on the either side of the median. Okay. So I would say the median is exactly where the mean is, because again, you get 50 and 50% of the values on either side of the mean. If you have symmetry, the mean and the median will be the same, which is sort of convenient. I like that. Okay. What if it's skewed? And I'm going to go with skewed right, like that. And I'm going to say, well, the median is the point of balance. And because it's a density curve or a density histogram, it's going to be like 50 and 50. It's going to be the median right there. On the other hand, where's the point of balance? Well, if you stretch out further enough to the right, you're going to have the point of balance is going to be a little bit higher because there's these couple values which if you think about this as a fulcrum, literally, they have a lot of leverage. I mean, literally the term in statistics is leverage, but you also learn it in a physics class. The way I like to sort of think about it is back when I was a kid in, age 4 and 5, you get a whole bunch of kids on one side of the teeter-totter, and they're right close up to it. And then you can balance it out with like one kid way to the far other end. It's going to balance. It's physics. The mean is the point of balance. And you can see the mean is going to be higher than the median because it's skewed. And if you want to think about it from the point of view of just today, I'm going to say you've got an income. I've got an income. Let's pick another person at random. Oh, Elon Musk has an income, or better, a wealth. Who knows how much income he has? But we each have a wealth value, and your wealth is probably zero, and my wealth is probably about zero. On the other hand, Elon Musk, 100 billion. No, she's $1 trillion today, and so the mean wealth of you, me, and Elon Musk would be like 300 billion dollars. What's the median wealth? It's either yours or mine, depending on whether you're coming from a family with money or not. It's going to be one of the two of us, and it's going to be close to zero. So what do we have here? A skewed distribution, in this case, skewed to the right. The mean exceeds the median. And so if you are looking at a histogram, and you can see that it's skew right, you're going to know the mean is higher than the median. And I guess if we use the opposite argument, we could say skew left distribution would have things the other way around. Any questions about that? Okay, so what I'd love to do is to move forward into discrete distribution. So we talked about summarizing data. What if you're trying to describe thing like the mean of a discrete distribution? So we're going to term the mean one of two things. The mean for a discrete distribution. Actually, let me redo this. For a distribution, whether discrete or continuous, I'm going to refer to the mean as mu. We said yesterday or 2 days ago when we talked about the normal curve, mu is the central value, and I called it an average. Yeah, literally, mu is a mean, and I could also refer to it as the expected value of the random variable x. Some people would even write mu with a subscript mu sub x, if you will. So, three different ways of phrasing the same thing, but you've got a friend out there named Robert, but some people call that guy Bob. Other people call the guy Bobby or Robbie. Just different names for the same thing. Now, for discrete distributions, what we have is a probability mass function. We've got the values p of x, or if you will, p the x is equal to lowercase x, sometimes written p of lowercase x. For our discrete distribution, I would say mu is just equal to summing over all the possible x times p of x. So let's talk about for a Bernoulli as an example. Again, let's go with the random variables that are well defined and understood. For Bernoulli, we've got x possible values and p of x. 0 to 1 can happen. 0 has a chance 1 minus p, and 1 has a chance of p. And so summing things up, I'm going to have, well, 0 could happen with chance 1 minus p, and 1 could happen with a chance of p. The mean is just p. So p is the chance of a success, but also the average value. I'm so pleased about that. It's such a clean little result. Any questions about that? Just sum up the chances times the possible values for each chance.
So did you say P is the mean?
P is the mean. Yeah, yeah.
Okay.
It's also the chance of a success, but it is also the mean. Goofy. Okay, so let's look at another example, and let's suppose what we're going to do is think through the numbers 1 through 12 and say each of the numbers 1 through 12 are equally likely to occur. So let's just list off the x's and chance of x. I'm going to do this horizontally because it's easier. 1, a 2, a 3, a 4, all the way up to a 12. Like, suppose people are equally likely to be born in any given month. January is month 1, March is month 3, month 12 is December. And if they each have a chance of 1 in 12 occurring, the average month of birth, if you will, the expected month of birth, or just mu, if you want to write it up that way, is just summing across all the x's their associated chance, which means, well, January with chance 1 in 12, February, month 2, with chance 1 in 12, plus all the way up to eventually December with chance 1 in 12, and that is 6.5, which says that if we're looking to find the average month of year of birth, yeah, average month of year of birth, if I'm choosing someone at random, the expected month of year of birth, if I'm picking a person at random where every month is equally likely to be chosen, that's 6.5. And that's a fun one if you think about it. Is anyone ever going to be born at month 6.5? I guess in some sense, if you're born on June 15th, but no, average of the number of the month. Yeah, 6.5. What about another example? Let's talk about the binomial distribution, and let's pick a fun color for binomial because we like binomial. I could say the random variable x is following a binomial distribution with parameters n and p. N describes the number of trials, and p is the chance of success on any one of the trials. And we know that the chance of any x occurring is just n factorial over x factorial n minus x factorial times p to the x times 1 minus p to the n minus x. Yes? And so what we need to do is to find mu, or sometimes called the expected value of x, and it's just summing together x times p of x, which, well, I'm going to write that as summing across the values. X goes 0 up to n, the possible outcomes, like flip a coin 12 times, 0 successes up to 12 successes. I'm going to have just x times, well, p of x. So that's n factorial, x factorial, n minus x factorial times p to the x power times 1 minus p to the n minus x. And so this is looking sort of gnarly, but I see something. And the thing that I spot here is an opportunity to do a little cancellation. So yeah, literally the fact that I've got an x here and an x factorial, I could do a little bit of summing. Yes? So, and to be honest, the case that x goes 0, that x out front, that just cancels out the first term. So maybe let's rewrite that. The summing of x goes 1 up to n, yeah, x times n factorial over x factorial n minus x factorial times p to the x times 1 minus p to the n minus x. That's n minus x. Apologize. Okay, so at this point in time, I'm going to sort of erase up top and sort of head up to the top and go with a different color to continue. So I think I'm getting most everybody good. And let's go for blue, maybe. Yeah, blue. Yes. So this should be equal now. Well, I'm gonna go with I'm gonna drop out the x. Yeah, I said you've x and an x factorial. I'm gonna rewrite that as well, summing x goes 1 up to n. Well, instead of x and x factorial, I'm going to put that denominator term as x minus 1 factorial, and factorial, and then n minus x factorial times p to the x times 1 minus p to the n minus x. So far, y'all happy with that? Okay. So I'm going to erase the green now and do a quick substitution. And let's do the erasing of all the green. Or most of the green, and go with a new color. And I'm thinking, how about purple? Let's go purple. So what I want to do is choose n star to be equal to n minus 1, yeah? Or if I go with n, I could have n star plus 1. Those are the same thing. And depending what I see over here on the right, I'm going to plug in n star appropriately for places where I saw n. Or perhaps I'm going to plug in an n. Yeah, so I'm going to sum here. Hold on a second. Okay, so I'm going to plug in n star here. So x goes 1 up to n, but well, let me do this. Yeah, I'm also going to want to sub in, I'm going to sub in y just for convenience. Y, I'm going to have x minus 1. So I'm going to put in a y every time I see an x minus 1 and an n star every time I see an n minus 1. Okay. And then also I'm going to go with y plus 1 for x. Okay, so now I could say y goes 0 up to n star. Okay. And I'm going to have n star factorial in the numerator. I'm going to have y factorial in the denominator. And I'm going to have n star minus y factorial in the denominator there as well. And I'm going to have p to the power y and 1 minus p to the power n star minus y. Okay, so and then oh darn it, and I need out front of that the whole thing n times p. In fact, I need to factor that out. I apologize. Let's put that whole thing instead of out front, I'm going to put times n p. Okay. So I'm going to say I trust that you could do the factoring and verify from blue to purple it matches. Damn it. Oh, I can't undo that. So what I'm going to do is sort of get back down to rewriting that thing in purple that I had just erased. I apologize. That's np times summing y goes 0 up to n star. N star factorial over y factorial, and then n star minus y factorial times p to the y times 1 minus p to the n star minus y. But I want to draw your attention to this term here. It looks as though this is well, it's the sum of all the binomial PMF values for y distributed binomial and star. I'm just making a mess of this. Y distributed binomial with n star trials and p as the chance of success. So that sum there must be, that whole thing must equal exactly 1. Which means I've got np times 1. So n times p. So I want to sort of quickly get to summarizing what that means. I'm going to leave this here for you to finish copying down if you'd like to. But it says that on average, if you're flipping a coin n times and p is a chance of success, let's think flip a coin 100 times. If the chance of success is 0.5, how many heads would you expect to see? Again, X is just the number of successes or the number of heads. If you're going to flip a coin 100 times, and it's a fair chance of success, 50% heads, 50% tails, N, which is 100, times P, 0.5, says you'd expect 50 heads. This is not surprising. This is, in fact, exactly what you would expect to see. The expected value is, in this case, quite expected. Okay. I think we took a bit more time on that than I wanted to, but I wanted you to see the cool math. I apologize if that took longer than it is awesome to take. Let's talk about the continuous distribution case. Okay, so the expected value of x, the expected value of the random variable x, which I could just write as mu or shoot mu x, if you will. All I have to do is integrate negative infinity to infinity x times f of x, yeah, dx, and we're good to go. So let's talk about x uniform. So if x is distributed uniform on the range a up to b, a up to lowercase b, I apologize if it looks like a cap of b, basically our distribution looks like that. So between a and b, all of the values that are possible are equally likely, and 0 beforehand and 0 afterwards. So f of x is plotted here along the y-axis. And we know, I'm going to switch gears to choose a color for yellow. Yellow, that total area has to be exactly 1 because it's a probability probability distribution function. So probability density function has total area of 1. I'm good. So f of x here, maybe choose a different color. F of x has to be 1 over b minus a for a x b. For a in the range a up to b, for x in the range a up to b, it's just 1 over b minus a, 0 OW for otherwise elsewhere. But we know that the mean is the point of balance. So that would cause us to probably suspect mu is at a plus b over 2. Let's see if indeed that is the case. I'm going to take a screenshot here. Any questions before I move on to the next slide or the next screen? Okay. So what I need to do is to find the mean, I have to do my integration. Okay. So the expected value of x, or I'll write that as mu, equals integrate negative infinity to infinity, x times f of x dx, which in our case is integrating a up to b, because outside the range a to b, the height of f of x is exactly 0, so we could ignore that part. X times 1 over b minus a, that's our density. The density is a constant, dx. And so we're integrating x, basically x itself, and then I've got that constant 1 over b minus a that I'm going to pull out front, and that's going to be x squared over 2 is the integral, evaluated at x equals a and b. So I've got 1 over b minus a times then 1/2 of b squared minus a squared. And if I remember, this is like frick, maybe around junior year, sophomore year of high school, you learned, b squared minus a squared, that's part of a thing. And if you multiply b minus a times b plus a, you're going to get b squared minus a squared. Okay. So I could factor. So b squared minus a squared over the b minus a gives me a plus b, and I'm left with just 2. So indeed, it is the average of the two endpoints is where we're going to find the point of balance. Yay! I'm excited about that. As a group, you guys are muted, so you're less excited. I can hear you all cheering inside your heads. Okay. Any questions about that? So what I want to do is move on to talk about variance and standard deviation. Okay. And this is chapter 2, section 2, and let's talk about variance and standard deviation. First off, I like to think in terms of standard deviation, but our book will sometimes use variance instead as a measure of spread of the data values or spread of the values in a distribution. Standard deviation sometimes abbreviated SD, is most often used. I'm going to give it a 2 checks and a happy face because that's the way we tend to speak. Variance is often done for theory or for, I'll just say, calculations. And it's inconvenient units. So literally, standard deviation squared is equal to the variance. So there you go. If I find a standard deviation, I'm finding the square root of the variance. If I find a variance, I could then take a root and get the standard deviation. So let's give you, for our data values, the equation for the variance. So the variance, I'm going to abbreviate that S squared. S squared for the variance? Yeah, S squared is the variance, which implies S would be the standard deviation. I take a root of the variance to get the standard deviation. That's 1 over n minus 1 times the sum of the individual data values xi minus x bar squared. So we already have an average. Well, how far away are the data points from average? Take those distances and square them and sum them and divide through by n minus 1. So first off, compared to average, where are you? How much taller than average are you? How much older than average are you? Compared to average, if you are younger than average, your age would be below X bar, you're going to have a negative deviation. If we square the deviation, we get squared deviations. And this is almost like, not exactly, but almost like an average of the squared deviations. It's
Professor,
that, yeah, yeah, please.
what does that say after the summation? X times negative mean? And the thing that says deviation above it or
Oh,
below
yeah,
it.
yeah. So right below, so the red bits, yeah?
Yeah.
Okay, so let's pick yellow and I'll sort of highlight things as I go. Xi minus X bar, then squared. So yeah, literally how far above the average are you? That's all we do. How far above average are you? And we'll take those distances, we'll call them the deviations, we'll square them. And then if I divide through by n, it's literally the average of the square deviation. But, in purple, I said, let's divide through by n minus 1. Uh, we'll call it a variance. And if you literally have the average of the square deviations, shouldn't you take a root of the squared thing? Yeah, that's why we call the standard deviation S. So I'm going to give you a quick example by hand because everyone needs to do this once by hand. I probably want you on your homework. If this data set size is not big, please do it by hand and then do the rest of them with the software or some other approach. Okay. So if I've got X values of just 1, 3, 4, 4, 5, and 7, and I'm picking these super conveniently, I'm just going to put them in a column 1, 3, 4, 4, 5, 7. First off, I need to know the average. And shoot, if I've got 4, that looks like the median, and 3 and 5 are just as far below and above the median as each other, 1 and 7 also. So this is symmetrical. The average X bar here is going to be 4. So let's write out a column for the deviations, X minus X bar. How far above average are you? Well, you're 3 below, you're 1 below, you're at 1 above, and 3 above the average. Those are the deviations. The square deviations, X minus X bar squared would be 910,019. And the sum of those values here, because that's the next step here, the sum is 20. And so the standard deviation, or I guess the variance, S squared would be just, well, I've got 6 values, 1 over 6 minus 1 times then that sum of the square deviations, 20. That's 4, but the standard deviation S would be then 2. And the way we like to think about standard deviation is what is the typical distance between a data point and then the average? And if the average here is about 4, some of the data points are like 2 away or 3 away. Some are 1 away. So it seems like some of the data points are at the average, some are 1 above or below, some are 3 above or below. The typical distance from average is like 2. It's not a perfect way to remember it, but if you basically think, how far are my data points away from average? You can solve for that. One last thing before the hour, and that is, what if your distribution is discrete or continuous? How do you find then the variance? I want to sort of quickly define it, but I'm not going to sort of do an example on this right now. The variance of X, or sigma squared, we define to be the expected value of X squared minus the expected value of X squared. That's a little goofy. But let's talk about the expected value of x squared. How would I find that? Literally the expected value of x squared, if it's discrete, the expected value of x, if I squared it, would be literally summing over all the possible values of x squared, what their various chances are. So indeed, you could find that thing right there, and you already know how to find the average x. You could square it and subtract out. For continuous, the expected value of x squared would be literally just integrating from negative infinity to infinity, x squared times f of x, the density, dx. So if you need to find those, yeah, I can. But our book has in the reading a nice little section on the Poisson and the binomial, how you would find their variances. But the lab today, no, shoot, the lab yesterday asked you with the Poisson to sort of figure out approximately what the variance of the Poisson was. And so you've seen numerically what I would have shown you next if I wanted to keep working my way through the book. But it is 5 o'clock, so another day, another dollar. And this being a Thursday, and a Thursday where we've already done office hours, I'm not going to be doing office hours formally, but if you ask me to stay a little bit, I will. Tomorrow, I have a couple things booked already and not yet put into the calendar, but you could always make an appointment to talk via Zoom. The limitations are have to be out of here by 4 p.m. tomorrow. And I do have a thing in San Luis, live in Los Osos, so there might be some travel time as well. But let me know if you want to meet tomorrow. Otherwise, I'm going to hang for a little bit and we will talk soon. Enjoy your weekend and we'll see you on Monday.
What did the DISC stand for again?
Discrete.
Discrete. Okay.
Yeah, that would be, well, continuous is every value in a range of values is possible. Discrete is no, no, no. You could list off eventually all of the possible values. I usually
Gotcha.
think of integer outcomes as discrete, but weight and height are not integer. Those are continuous.
Right. And when you said the standard deviation was 2 for that set, that was an approximation, right? It's close to like 1.826 or something like that.
For which
You gave the numbers 1, 3, 4, 4, 5, 7.
Oh, no, no, no. 1, 3, 4, 4, 5, and 7. The standard deviation is exactly 2 if those are data values. But hey, here's the fun thing. You sounds like you probably calculated the standard deviation with an n in the denominator using your calculator. That's sort of another way it could be done. And
Oh, I should do it with
because
n plus 1, right?
n minus 1. Yeah.
N
So
minus 1, yeah.
the n minus 1 approach that I said we would use is going to be if you have data, the approach you were using is going to tie to today's lab and why we do use an n minus one. It literally is a better estimate of the standard deviation of a population that I'm sampling from. And you'll sort of
Right,
explore
because
that.
okay, that makes sense because we don't have the what's it called? We have don't have the actual standard deviation of the population. We have the standard deviation of our sample size, so it's not
Yeah.
exact. Okay, gotcha.
The standard deviation of your sample size, if you used n instead of the n minus one that I'm suggesting, would be a misestimate. It would be an underestimate of the spread, really.
And
Um,
what's the official name for the sample standard deviation? I feel like there's a name for that.
Sample standard deviation.
Okay. Is there no other name? I don't know. I took a stats class in high school, but I'm trying to remember back 2.5 years now.
Yeah, no, S is the sample standard deviation. And it's if you have data, you're
Standard
gonna get an
error? Is it
S.
standard error or
Nope.
is that something
Nope, nope,
else?
nope. Standard error is something we'll get to next week, I think.
Gotcha. Okay.
And standard error is not a bad term, but it's like how much error would we have if we're using something like a standard a sample mean to estimate a population mean? How far off could I likely be? That's a
Hmm.
standard error. Standard deviation is a measure of spread of the data values in a list of numbers.
Gotcha. Okay, sounds good. I'm just trying to, I have like the little holes for my that I remember from high school. I'm trying to fit everything all in together still.
You know, it's one of those things. It's like I was talking to
Yeah.
someone earlier today, and I say, I haven't ridden a bike in 4 years, but I know if you handed me a bike that worked, I could get on it and ride.
Mhm.
It's that thing exactly. And like completing the square. I would probably struggle with that for a little bit, but I could get it done.
Right. Yeah. Yeah. Anyways, thank you.
Yeah, sounds good. We'll see you soon. Bye bye.
Yes.